Hello, we are Group 3. Our senior project is on worst case discharge calculation using production modeling tools. In April 2010, the Deepwater Horizon rig had an unfortunate blowout, which is very catastrophic. Since then, industry members have put on intense regulatory measures to make sure that this event would never occur again. Since then, the Bureau of Ocean Energy Management has required a worst-case discharge calculation to be provided before drilling any offshore well. BOEM has defined worst-case discharge as the single highest daily flow rate of liquid hydrocarbon during an uncontrolled wellbore flow event. A few of our goals this semester have been to first create a workflow model using the IPM softwares. We use Prosper, MBAL, and GAP. Once we learn how to navigate those, we then use these different flow correlations to test different reservoir qualities. We actually measured different scenarios such as cumulative oil production, gas and water production, average oil rate and production, reservoir pressure, and aquifer influx for each of the reservoirs and with the different correlations. After that, we'll take all that data and compare it to each other with the different flow correlations. We then plan on testing different parameters such as rock compressibility, changing our aquifer model with all the different flow correlations. We'll then analyze all that data and we'll then use it in our final presentation and our report for industry members.
Some of the main objectives we have this semester was to run the simulations using the 8 correlations. So each one was run for 60, 90, and 120 days. And after running these, we then generated graphs to show such things as cumulative oil production, cumulative gas production, average oil rate, reservoir pressure. After we finished all the correlations we were running, then we then compared all of them together on certain graphs such as the cumulative oil production, as we'll later see. So at the beginning of each simulation, so we have our basic GAP file, and within that we open Prosper and change depending on which VLP we're running. So we'll change, if we want to run Haggard and Brown, we go in there and change that and calculate that data. And then we go back into GAP and then generate the IPRs and the VLPs. After that, then we're going to run the prediction based on the 60, 90, or 120 days. And after running that, then we're going to generate the graphs for the total system. So such things as the cumulative oil, cumulative gas, average oil rates. And then after that, then we're going to go into the tanks for the 7-layer system and generate plots for reservoir pressure, average oil and gas production, and such things as that. And then after we have a total of 14 graphs and Excel data for each correlation for each time step, then we're going to, at the end, after we run all of them through for each of the correlations and each of the times, then we're, like I said, at the end going to compile into certain graphs all of the correlations to compare and contrast, see how they correlate and see what's different. As you can see in this graph where we have cumulative oil production for 60 days, we have all the 8 correlations, and you can kind of see that the Duns and Ross original one is kind of the outlier, while most of them kind of follow this general curve right here. And then for the average oil rate for 60 days, as we compare all the 8 correlations, you can see again that the Duns and Ross original is also the outlier, while the others kind of follow the same pattern.
So for the discussion of our results, we found that the Duns and Ross original correlation was not generally applicable for multi-phase fluid flows, especially those involving a water cut. So this tended to over-predict the cumulative oil production as well as the average oil rate, as you saw in the previous graphs, which are shown here again. As you can see, this gray line represents that flow correlation. We also found that the Haggard and Brown correlation over-predicts for heavier oils and tends to under-predict for lighter oils. So that tended to be somewhat higher as well, as seen here. And so we found the most applicable correlation to be Beggs and Brill. It tended to be the most conservative. It's also good for multi-phase fluid flows, as well as those involving water cut, and anything with an inclined wellbore geometry. So that was the lowest line on this graph, indicated by the light blue here. And so the application of worst case discharge, ultimately we want regulatory agencies and operators to have an idea of any new well they drilled, how much hydrocarbons could flow out of that well. So they need a consistent method for calculating worst case discharge that provides reliable and accurate results every time. So this could be a single correlation or a suite of correlations, but ultimately the accuracy of those correlations and of the model depends on the input data. So there also needs to be a standardized form for that input data. So the accurate and well-reported data inputs, along with a good working model, will ultimately lead regulatory bodies in industry to be able to better anticipate and regulate blowout events. So BOEM has devised a worst case discharge section on their OCS plan information form. As you can see on the first page of this form, they ultimately want you to report the total volume of worst case discharge. And as we go through some of the other forms, you can see they get a bit more complex, ultimately requiring geologic data for the well that you're drilling, along with analog wells in the area. And then we get into some of the more engineering data, things like the flow correlation used, different turbulence factors, and then ultimately rock and fluid properties from the various pay sands that you'll be going through. And so here we can see some of the data reporting for the various pay sands, different rock and fluid properties.
So to conclude, the difference between the different flow correlations needs to be further analyzed so we can have a better idea of which correlations or what group of correlations can be used to give us the best results or the most accurate predictions for worst case discharge. Also, our model can be used to simulate varying reservoir or rock and fluid properties to better understand how those rock and fluid properties affect the flow rate. And in the future, we can do those tests where we vary, say, rock compressibility or average reservoir pressure or bubble point of the oil in order to see how that would affect the worst case discharge calculations, because the flow correlation are not the only factors that affect the performance of our results. And also we want to give an acknowledgement and a special thanks to Dr. Gupta, our faculty advisor, Florencia Vasquez, who's been very helpful in helping us use IPM software. She's a master's candidate under Dr. Gupta. Also, petroleum experts for providing us with the licenses to use their software. And then Kraft and Hawkins Department of Petroleum Engineering, all of the faculty, Dr. Maleva and her TAs, and also the LSU College of Engineering for all of their support.